Today what we're going to be doing is look at some of the depositional environments that feature the rocks that you started looking at in Tuesday's lab and what you will continue looking at in today's lab. Now we're going to look today at two depositional environments. I'm going through these ones fairly quickly. If you recall, last time we did this, it was on beaches, and we just talked about beaches. This time I want to talk to you about alluvial fans. You've all talked about alluvial fans previously. At least you should have. In Geology 111, if you recall, this is where the arcoses and breccias were always associated with. Now, depending on who you had for your instruction, it probably involved more or less saying, it occurs in the mountains, the end. Or if you had me, it occurs in the mountains, here's a picture, the end. Now we're going to look at a little bit more detail in terms of what the facies look like. And I also want to talk to you about a couple complications involved in every aspect of science in terms of writing things up. If you recall, and if you've got your grade size projects back now, many of you got the note in your results, don't mix results with interpretations. That's very important. Interpretations are based upon your results. They are not mixed up in the same thing. And yet, a lot of the stuff I've showed you when we're talking about things like facies, I show you the results, and right beside it is the interpretations. And unfortunately, that's one of the things that we're all guilty of. I'm going to talk to you about a way that we used to deal with it and why we're not dealing with it in the same way as much anymore. Then we're going to talk about braided streams, simply because braided streams are uber cool. And let's face it, if you want to find gold, if after a couple years of making $150,000 a year in the oil industry, you decide Houston really does suck, and it does, and you say, I got to get away from it, and you decide, I'm going to Alaska with a sandwich and a backpack and a good pair of hiking boots. You going to go pan for gold? I'm going to show you how to go and find places to go pan for gold, okay? All right, last time we met, we were talking about immature siliciclastic sediments and sedimentary rocks. We introduced the siliciclastic sediments, and we looked at how they basically are distinguished from one another. Then I introduced point counting for you as well a little bit. Now, if I'm not mistaken, Cole, you weren't here last week, were you? Okay, well, my rules are I don't go and stick on people who weren't here to go over the reviews. So I guess we're going to start down this side. George, do you care to summarize the following slides? You were here yesterday, right? Or on Tuesday? Okay. Significance of this, please, in terms of what we were talking about on Tuesday.
It deals with most of the immature siliciclastic, not really immature, but ignore half of what I said.
That's okay. I ignore most of what I say, so you're fair company.
And, it deals with, it's a ternary plot, deals with the feldspar and the rock fragments mostly, and then the quartz is up at the top. And because they're immature, they're going to be more angular sediment?
No, don't jump, okay? Because remember, the diagram here is just summarizing compositional variations.
Okay.
Now, again, the thing to note here is that we're using the same ternary plot that we use for mature sediments. And again, it makes sense. Siliciclastic sedimentary rocks are defined as those rocks that have the silicate minerals in them. And again, we're using QFR calculations because we want to have consistent means by which to compare things. So last week you dealt with the stuff that plotted more or less right there. Maybe a little bit on either side of this, but more or less right there. Now, when you deal with the immature field, you have material coming in from different sources. So the primary ingredients here now are not necessarily going to be quartz. They're going to be
feldspar and rock fragments.
Which means you better have a handle on how to identify the different feldspars and the rock fragments, which is why we went into a little bit detail about stuff. Now again, for those of you that have not had mineralogy or are not geology majors, I'm going to assume that, and you have to understand that this is something that takes time, right? So I don't expect anybody who's never seen microcline under a microscope to immediately understand this microcline. For those people, you can basically get away with just calling it a feldspar, okay? So when you start looking at these things in some detail, I will show you the different feldspars, but frankly, it's not that important if you don't get them all. But for the rest of you, the difference between a good geologist and an okay geologist is whether you look at something and say it's biotite, muscovite, phlogophyte versus mica. And if you tell me it's mica, you're going to get a little X beside it and say what kinds. All right? So now again, this takes a considerable amount of time to actually learn how to do this, but you start doing it now, and the more you do in this, the better you're going to get at it, okay? Now, here's where you can start talking about the grain size attributes.
Well, the top one would be, it's a series of diagrams. It would be grain size rounding and sorting, and it would go left to right, coarse and very fine, on the grain size, and that deals with transportation. And then the rounding also deals with the age, not really the age, but the mature to immature rock, and angular would be more immature, well-rounded would be more mature.
Okay, now be a little bit careful again in terms of what maturity is. Maturity is based upon what?
How much has been...
No, it may not be this diagram that's your answer here. What's the maturity based upon? Composition. Okay, remember, maturity has to do with how much weathering has taken place. These diagrams here aren't necessarily maturity. They have to deal with things like energy, degree of wear, and again, energy. So the thing to note here, and I'm glad that we're having this discussion here now, and it's always, and one of the reasons why I like to have students kind of summarize these things is it allows me to remind myself to point out important differences. Maturity has to do with composition, where you are in proximity to the source of sediment. These have to deal with how the sediment gets from where it was to where it is today. The further you transport stuff, the more likely this is going to occur, right? This has to do with the nature of the source or the energy where the stuff ultimately gets to. So if you're in a quiet water environment, you may be in a quiet water environment thousands of kilometers from where the source of sediment was, so it's going to be mature sediment, but it's going to look like this or like this because that has nothing to do with maturity. It has to do with other variables. Remember, in nature, there's a whole bunch of overlapping components that affect the things we are. And that's a good cautionary note, because far too many people, when they look at something, have one or two possibilities in their mind. And they don't consider that things are much more complex to that. If you end up being one of these people who only looks at this as being black or white, you're going to find yourself usually making mistakes. The world is full of shades of gray, in other words, okay? All right, and this was, of course...
So immature silicic classic sediment, and that's across nickels, so it deals with the grades of feldspars and rock fragments.
Why does this look different from the one from mature rocks?
It's not heavily quartz, it's other stuff.
Right, and the idea now with all this different color patterns and all, and I hope you appreciate my selection of different palettes from the PowerPoint 3 palettes available things. And some of you by now have seen this versus this versus this. This is supposed to be chert. This is supposed to be... no, it's too parallel. So I'd say plagioclase. There isn't a microcline palette in PowerPoint, I'm afraid. And of course, this refers to more birefringent minerals, etc. The point is, if you have more varied minerals, you would expect to see more varied appearances in a thin section. And since most of you have already looked down a thin section or microscope at these things, do you agree they look like a lot more variety than the first thin section we saw? How many of you felt like, oh my God, what am I in for? Yeah. All right. And this is, by the way, the hands that went up for all the geology majors, or for the most part. Okay. Yeah, it's a lot more complex. But the point here to be made is that even though it looks a lot more complex, what you do is you zone in at one thing at a time, and after a while you realize that the principles you learned previously apply. Look at the properties, use the properties to resolve just what exactly the minerals are in thin section, okay? All right, and then we start talking about lithic fragments, and this is the R component. So without going into detail of reading everything and all, why was this slide put up? What was the purpose of me actually putting this one and the one that followed up?
The detailed difference between plutonic and sedimentary fragments.
Again, you're reading it. Why are there fragments up here? What is the significance of rock fragments? What do rock fragments allow you to determine?
The origin of the rock.
Very good. That origin incidentally has a specific term. It's called provenance. We don't go into provenance too much here now, but I can tell you, if you look at stuff and you get a good idea of what the rock fragments are, you can determine an awful lot about the nature of everything. For example, when I was doing my PhD in New Zealand, there were a lot of gray wacky rock fragments. Gray wackies are a type of dirty sandstone, as you know. There are also significant numbers of volcanic rock fragments. all of these rock fragments came from sources that were kind of dumped into the area. And when you look into those combination of things and realize they all have to be coming from the same overall source, it allows you really to imagine what the whole region was like at the time that sediment was being deposited. All right, so plutonic rock fragments, sedimentary rock fragments, volcanic rock fragments, and metamorphic rock fragments. In looking at your thin sections on Tuesday, I saw representatives of all of these scattered amongst the thin sections you were looking at. Do not expect to see every single one in every single thin section. I mean, you shouldn't, if you think about it, unless there's a very mixed source of sediment. Some of the rock fragments you've seen in the litheronites you were looking at, dominated by chert. By the way, chert is a sedimentary rock fragment, as it turns out, usually caused from the silicification of limestones. I saw volcanic rock fragments. There were some interesting metamorphic rock fragments. I think, who had the, did you have the, you had the rock fragment, the quartzite, right?
I had that.
Yeah, with quartzite with a little bit of foliation still preserved. I think it was you that had it. Right? Yeah, so anyway, look around, and I will continue if I see something really good to let everybody know about it, okay? And then, I'm not going to ask you to go over these things, but again, just a reminder, and for those of you that certainly weren't here, and several of you weren't, this is the type of thing you're going to be seeing under a microscope. This is an Arcos, and there's a lot more variety in here as well, too, okay? All right, so thank you. Today's discussion, we're going to talk about where some of this immature siliciclastic sediment ultimately ends up by talking about depositional environments. Once again, what we're going to do is look at both ancient and modern environments. I'm going to focus primarily on the modern environment for the braided streams, because you guys haven't really had a chance to talk about braided streams before. For the alluvial fans, we're going to talk about more in terms of interpretation of facies, etc. So today our agenda is going to be as follows. I'm going to give you a pictorial overview, first of all, alluvial fans, and then I'm going to talk about alluvial fans, and then we'll talk about braided rivers. So let's start with the picture show to start with. One of the nice things about being in an airplane, or used to be in an airplane, it's a bit of an issue now. For example, you're not allowed to use electronic devices, including cameras. I'm not sure if you knew this or not, when you're in an airplane when it's taking off or landing, which makes taking photographs a lot more difficult. Back in the good old days with slide film, you could just sit there and take as many photographs as you want because it didn't apparently cause the airplane to crash and blow up, which is what they tell you when you take a photograph in an airplane. But I used to always sit beside windows, and I still do when I have a chance, because I like to look out of airplane windows when I'm flying. I get to see things. And if the windows are clean, you can actually photograph them. So this is a shot that I took while flying between Nevada and California, I guess. And what it is an overview of the Sierra Nevada mountains, and it's showing you erosional features, depositional features, and a lot of nothingness, because this is the Sierra Nevada mountains and it's a dry region, okay? This area here that you're looking at way off in the distance, there's a close-up of what it looks like. What you're looking at is basically a pile of sediment that is being deposited at the base of a mountain. There's actually several piles of sediment, one coming from this direction, one there, and then there's this. This is a complex environment that actually consists of 3 alluvial fans and what would best be described as a braided river floodplain. This is the braided river component. This is flatter than the alluvial fans, which are significantly steeper. By the way, I have no idea how big that is. My estimate is that you're probably looking at something that's probably on the order of maybe 6 or 7 kilometers across in this direction. 6 or 7 kilometers is like 4 or 5 miles. Relatively large. But this pales in comparison to some of the alluvial fans that exist today and have existed in the past. This is another lovely shot. This one I really like, because what you're looking at now is an alluvial fan as it merges into a standing body of water. Now this again is in the California and Nevada area. I'm not sure where this is. That's an artificial lake, I can guarantee you on that. But the nice thing here is that you can really see the conical shape of this depositional component. That's the neat thing about alluvial fans. They do have fan shapes to them, okay? So this, and this all represent possibly actually lake levels. So this lake's probably going up and down. That shows you where in the overall shape of things. I'm going to pan out here a little bit to show you that what you're looking at now is a relatively complex system that consists of a narrow feeder channel system, which is often a braided stream system as it turns out, and then where you actually get deposition, it fans out, and sediment that was funneled down through the pass here tends to spread out and is deposited in this fan shape. Let's put a few names on some of these things, okay? When you're looking at fan structure, it's relatively simple in terms of the naming scheme. So looking down now, so this is the channel that feeds into things. This is called the fan head. This is the mid fan. And this is the fan toe. All right, so here's the toe component. There's the mid-fan area. There's the fan head region. Now what you see also here is what I call the alluvial plain. In cross-section, if you look at this from A to A prime like so, fans generally form at sudden grade changes from a mountainous area to a flatter area. And the fans themselves tend to have a very convex shape to them. So there's the head, there's mid-fan, and there's the toe. And eventually what happens is the toe passes into a flat area that's not part of the fan structure itself. This usually just called the alluvial fan, or alluvial plain. That's where rivers, etc., start to flow down. Okay, so this just possibly gets into the plain component here. Here's another shot, and this shows you the structure of the feeder channels. So here is the fan. Notice you have valleys, water pouring down from the mountains, gathering up into one central part or one dominant channel system, and then once you hit the fan again, it spreads back out. If you know anything about rivers, you know that this basically imitates or mimics the whole idea of tributaries gathering up water to give you a very large river system, and then once you get to a deltaic area, it spreads back out into distributaries. The same dynamic occurs within an alluvial fan system, and it has to do with the same processes. Here we have a steeper gradient. When it rains heavily in this area, water pours like crazy, gathers up in the central channel, but once that slope changes, the speed of the river system slows down, and then you start depositing sediment like crazy. So basically this is like an on-land delta in terms of analogies. A couple other shots too. I love this one here because just shows you just how wonderfully different things can be over short distances. There's nothing wrong with this image. This actually is a legitimate color variation. The rocks that are here are dark. The sediment that is here is light. So whatever these rocks are here now, they are just darker in color. There's no shadow over this at all. This is an alluvial fan network. You can't see it very clearly because my camera tries to bounce off everything. But if you look very carefully, you'll see there's the gathering up, then there's the distributing. So here's the actual fan structure. Everything that is in here actually is a completely different sediment, a completely different system entirely. The alluvial fans are depositing sediments in this direction. Anything that's preserved in terms of paleocurrents, in other words the direction in which the sediment is moving, is going in this direction. Everything here is caused by wind. So it's a secondary system. This is basically a desert. These are dune systems associated with the wind blowing things. You can imagine if you were to find this stuff preserved in the rock record, how much of the heebie-jeebies the geologists would have trying to figure out why in some direction water's going this way, but in another direction things are going that direction, 90 degrees removed from it. If you're a good geologist, you'd be able to interpret this as two overlapping depositional systems. By the way, this is the reason why we have a problem with water in the southwest of the United States. Somebody decided they were going to farm here, and they probably had a lot of irrigation going here at some time in the past. The water was probably come from groundwater or from some sort of a reservoir, and of course it doesn't look like it's very good right now. In fact, if you look very carefully, you start to see some of the dunes are forming over here as well. Don't farm in the desert. If you're going to do it, use a damn greenhouse. And this is one last shot I'm going to show you in terms of pictorial views of alluvial fans. This again is another area where irrigation seems to be more successful here, right? These are all irrigated sections. Give you an idea of scale, you're probably looking there, those look like quarter sections, so that's a mile by a mile in size. This is a very large area showing you coalescing alluvial fans. There's more than one alluvial fan in here. In fact, if you do the counting here, you'll be able to identify 1, 2, 3, 4, as far as I can see, and there's probably more in there. Now, each one of these fans, if you do the math on it, looks to me like it's at least 6 or 7 miles across the base. And if you start adding them all up together, you can see that you're looking at a depositional system that's consistent in terms of the environments that goes on for what? Maybe 15 miles along the base? And that's just this portion of the mountain ranges that you see here. Alluvial fans in the past have been huge dynamic systems. All right, so let's just talk now about alluvial fans and what they're like. This is a view from the top. This is a shot I took from New Zealand, and this is kind of a neat area. There's a glacier right behind us. The glacier is melting, and as it melts in a mountainous area, water pours off of it and is transporting sediment from the glacial valley downwards. So this is actually a very large alluvial fan tied into a glacier. And the neat thing about this is, there's a road going up here. You don't even realize you're going uphill. At the toe of alluvial fans, the gradient is so low, you don't realize you're going uphill because you just have a very shallow grade. It's only when you go to the top, turn around, look back, and you realize, oh my God, I can see halfway across the island of New Zealand. That's a huge gradation increase. Yeah?
Does the melting of that glacier, would it cause tectonic activity or anything from bouncing back?
No, not. This is a small alpine glacier. A continental glacier can cause issues, but we're talking about 4 miles of ice the size of Canada. All right, this is nowhere near that big. All it does is just wash out some hobbits every once in a while, but you find them, they get back home. Nobody's paying attention. Anyway, here is, again, the ever-popular block diagrams. This, again, is from FASE's models that shows you essentially how they relate to three-dimensional networking. Okay, so here we have mountainous areas. Here we have alluvial fans. I want you to note here the identity or the identification of the distributaries or the feeder channels that come off of the alluvial fans. Little dots you see here, circles, are for coarse grain material, gravel sized. As you get away from this, you notice you don't see a lot of gravel. Instead, what you see is sand. Notice the alluvial plain, in this case drawn 90 degrees to the direction of the orientation of the fans. These things are also important because we're going to come back and talk about this. This is our one opportunity to talk about mass flow again. In general, the sediment that makes up the majority of alluvial fan deposits tends to be gravel to clay sized. Heavy emphasis on the gravel size, especially in the head area of the fans. Angular to sub-rounded. And the reason here is simply that most of the grains are coming right off the side of the mountain. They get fragmented during frost heaving and other processes. They don't have very far to be transported before they ultimately get deposited again. Net result is mostly angular to sub-rounded grains. And again, because the source of the sediment is basically where the stuff's being deposited, there hasn't been enough time for major weathering processes to have removed all the immature components. They are heavy on feldspars, especially when you consider most alluvial fans are going to be in mountainous areas, and most mountainous areas are going to be associated with granitic rock bodies. Granites have a lot of feldspar in them. You would expect to see that type of mineralogy here. Okay. Now, here's some things you may not know about alluvial fans. Despite what you might initially think, because water is an important variable in here, most alluvial fans actually are developed in arid regions. The reason here is that while water does transport most of the sediment from the source down to the base of the plateau or the plain that the fans are forming on, it is periodic rain. If you've ever been to the desert, you know it may not rain for 2 years, but when it does rain, you'll get 6 inches of rain in about 10 minutes. That causes a lot of sediment to be washed down the sides of the mountains, to be literally washed in flash floods over the sides, get deposited instantaneously, and then nothing happens again for another 2 years. They are also best developed in tectonically active areas, and this should not be as much of a surprise to you. If you consider that we're talking about this type of topographic difference, where you go from high to low, unless there was some constant uplift in this area, erosion would gradually take this off and if you don't have that grade difference, you don't get alluvial fan deposition. So in general, the best alluvial fans always occur when there's uplift, where the mountains are continually being uplifted, as demonstrated by this diagram here. And they also demonstrate a very pronounced lateral fining. Coarsest stuff is always in the closest vicinity to the mountains or the source, or if you wish, in the highest or steepest areas, and as you get further away, it gets finer and finer and finer. Remember, the toe of the alluvial fans eventually passes into the alluvial plain, where you literally are depositing things on a gradient of virtually zero. All right, so they're primarily formed through the action of water flow. So when the rains, water is washing stuff down, but you also get significant amounts of mass flow deposits. Remember when we talked about mass flow? When we were introducing the way sediment can be moved? It can be rolling, bouncing, sliding, suspension, and then we talked just briefly about the different types of mass flow deposits. Well, here's where we have to come back and talk about it again, okay? We have different types of deposits that are well worth mentioning here to explain one of the most obvious diagnostic criteria of alluvial fan facies. Let's consider these in a little bit more detail. First of all, let's talk about debris flows. Debris flows have the highest sediment to water ratio of any of those mass flow deposits. Now, debris flows generally occur on the steepest parts of slopes. And since we're focusing in on alluvial fans, I'm going to continue to talk about alluvial fans, but please note that debris flows can also occur in non-depositional areas they're called landslides. What happens here is you have a lot of material that is being deposited in a very precarious slope area. If it rains heavily, what happens is the whole area gets saturated. Now, this is not water flow. It's not water causing the stuff to move. But what happens is, because you're in a high slope area, the material fails. We call it a landslide. But in this case, what happens is the material oozes down the hill and it kind of rolls around and slides. And what happens is it just literally continues to move until that instability is gone. Debris flows like this may only go a few meters. Or they may go further if they're more unstable. And often, once they stop flowing, water will continue to move out as it dewaters. All right? Now, these things usually are responsible for transporting anything. You don't need to have a confined or restricted grain size. Instead, what will happen is anything that's in there gets transported down. So they generally have very large blocks in them, boulders even, and they do not show any sign of deposition by water currents. Sometimes they actually show rollover features. I literally have seen stuff that's rolled over like a Twinkie as a thing comes down the hill. Fluidized flows are more like this. If water is in a higher ratio to sediment, what will happen is material will come down and it's more of a fluidized flow. It's liquefaction. Remember that liquefaction we did when we were at the school last weekend? Or the weekend before, or whenever, I can't even remember when it was now. All right? What happens is, if that gets fluidized, it will flow down, and it tends to be a little bit better sorted. And then lastly, sieve deposits, which I mentioned to you once before. Sieve deposits are largely gravel beds that came down as a water-deposited current. So they tend to have very well-sorted gravel. But because it's gravel, there's a lot of porosity between it. If another fluidized flow comes down, what will happen is the sand will wash down through the sediment, and you'll get this mixture of well-sorted sand as matrix and well-sorted gravel as the coarse grain components. Sieve deposits are called sieve deposits because if you happen to be in an alluvial fan and you have a fluidized flow come down, you'll often see the water and the sediment flowing down, and it doesn't go any further. It just vanishes into the subsurface. Some people have inadvertently considered that to be, a cave deposit below. It's not. It's just because the porosity of the grains and the gravel is so high, water just washes down into it. Okay, so a lot of these things occur. Now, where do they occur? Primarily in this part of the fan, in the fan head component. The further you get away from this, the finer stuff becomes. Okay, so this is a cross section that shows you grain size variation based upon blatantly obvious symbols. Because this allows me to talk about one of the issues that I briefly introduced you to previously: the mixing of results and interpretation. Everybody who's ever done a detailed sedimentary analysis of an area is faced with a dilemma. When you're describing what you see in the field, you have to describe the different facies without interpreting what they are. So the question is, how the hell do you do that without naming them for what they are? And so far, when I've been teaching you this stuff here now, when I showed you the facies, if you remember when we were doing with beaches initially, I said this is the shore face facies, this is the offshore facies, this is longitudinal bar facies. That's interpretation. One of the ways that we used to do this, and this isn't very common anymore for reasons I'll get to in just a second here, but one of the ways we used to do this was to come up with a naming scheme that was not by itself interpretive. This is a summary table dealing with an interpretation of alluvial fan components, and it's from Walker's Facies Models book. And what they opted to do, and what I have to admit I did when I was a student, because Walker was one of my thesis supervisors, James was the other one, was to literally adapt this policy. What they did was they came up with an idea of defining the facies, in this case, based upon grain size. Notice the capital G here? That stands for gravel. Everything that's up here is a gravel facies. In fact, let me just go to the next slide to prove that to you. So there's the gravel facies. That's the code that they used. This was how they described the facies. For example, GMS is massive matrix supported gravel. The sedimentary structures, grading, meaning that it was coarser in the bottom, finer in the top. The interpretation is debris flows. All right, so this allowed you literally to go through the entire thing and say, here's all the different facies based, in this case, on the differences in grain size, and then put the interpretation here afterwards. You don't mix descriptions, results, if you wish, with the interpretations. But the real issue with this, and the problem that we've all faced since that time, is nobody remembers what the hell these things are. I remember what a debris facies is. I know what a debris facies is. I can remember what that is on a diagram, but remembering the damn codes is freaky, especially when you have a lot of different facies. Now, this isn't very bad. I mean, there's gravel facies, 5 different gravel facies. Looks like there's about 8 different sand facies, and there's a bunch that are down and through here. There's even a little bit of carbonate in there as well. But this is for a simple system. And even though an alluvial fan may be huge and complex, an alluvial fan is an alluvial fan. They're all telling you the same thing. When you get to the real world, and if you're describing a sedimentary section that might be 1,000 meters thick, like I had to do for my PhD, it's not just an alluvial fan. What you've got is about 10 different depositional systems. And each system has multiple facies in it. And some of the facies that might be marine have the same sand components as those that might be non-marine. So how the hell do you keep them all apart? In fact, this is a dilemma that I gave up on with my PhD. When I published that, I just said at the very beginning, I know I'm not supposed to do this, but I have no bloody choice. And the people that reviewed it agreed. Thank God, or else I would still be writing that paper. It was complex. All right. So the idea now is, this is how we should be describing everything that we see in the field. And from this, we can say that GMS, given its location, distribution, and characteristics, is interpreted as a debris deposit. In fact, there should be the first diagram, and then there should be an identical diagram below that, instead of having all these GMS things, has instead debris flow, fluidized flow, basically channelized flow. You guys will face the same dilemma probably when you're doing it, and I have no absolute solution on this. All right, so there's the debris flows, channel deposits, and again, remember, we have those channels coming down. Those channel deposits will be very similar to braided streams, and I'll talk about those shortly, so I have to go into details. And then once you get towards the end, you're dealing with those alluvial plain deposits. Now, looking at some of the alluvial fan deposits in the rock record, alluvial fan deposits have been dated in the rock record back to 3+ billion years in the past. We've known that depositional processes like this have been on the planet ever since mountains were on the planet, and they are largely, or they can be preserved because their characteristics are so blatantly obvious. There are very few places in the world where you can get combinations of relatively poorly sorted sediment that is immature, angular, associated with deposits involving currents. Consider the alternations that you would have with debris flows with channels cutting through them. And then, of course, as you get further down, you start finding more and more sedimentary structures associated with the finer sand deposits the way you get further down. Those sieve deposits I told you about are absolutely diagnostic. You see a sieve deposit, it's got to be multiple flows. And where are you going to find where are you going to find gravel-sized deposits overlaid directly by sand deposits? It's got to be someplace like this where there's a sudden slope transition. Now, the only variables you might have in terms of interpreting alluvial fans with anything else is going to be submarine fans. Submarine fans are very similar to alluvial fans, except for one important difference. These are deposited on land. Submarine fans are deposited thousands of meters below sea level. All right, and that should give you the major clue right there in terms of the differences. If you have water as a medium by which deposition takes place, you can still have debris flows. But you also have debris flows that pass laterally into turbidites. And we talked about that previously as well. Underwater landslide, if you have water getting mixed into the landslide, it keeps it fluidized, and eventually a debris flow can trigger a turbidite. Turbidites cannot exist in this type of environment. So if you start finding channelized deposits interbedded with turbidites, it's submarine. If you don't see turbidites, but instead find angular fragments, the fact that they're composed of immature sediments helps out here too. You know you're dealing with alluvial fan deposits. Okay? So the thing to note is this variety of coarse-grained materials and fine-grained materials. The best alluvial fan sequences I've read about are on the east coast and west coast of Greenland, where those sections, courtesy of the ice removing all the trees that might have covered things up, go on for thousands of meters in terms of vertical thickness and for many miles laterally. It's a wonderful place to go. We should go there. Actually, we do need a field trip to Greenland and Iceland too. That'd be a great place to go. I mean, it's going to feel like Greenland when you're up in Chiha this weekend anyway, so you're going to be prepared for it. What do they look like in the field? Well, when you guys have a chance, when you start working for companies, always encourage them to send you to conferences, because the more stuff you hear, the better off you're going to be. And most conferences have associated with them field trips. This was a field trip I took when I went to the GSA meeting many, many years ago, and it's to an alluvial fan sequence. I believe it is pre-Cambrian in age, somewhere I believe in Utah. It's somewhere in Utah, because I remember we couldn't get a damn drink after the meeting, after the field trip, because it was damn Utah. Nothing really against Utah except that you can't get alcohol anywhere. This is a wonderful single bed. And even from that distance from there, you see the big boulders here? I mean, that's the size of a human being. So this is one single bed of huge brecciated conglomerate. It's all tilted. This is not the original depositional slope. The whole thing has been tilted because it's in a tectonic area and all, okay? Wonderful example. That's beautiful examples of spherical weathering, but again, you can see the big coarse gravels. Here's a person standing for scale, coarse gravels with finer grained sediment in between it. The color is dominantly red because weathering of these sedimentary rocks in place is carrying on to this day, and because these were immature sediments, they contained a lot of ferromagnesium minerals like biotite, etc. The biotite breaks down in place while deposited as these beds into iron oxides, giving it the classic reddish coloration. The thing to note about alluvial fan deposits is the sudden transition that you get from one type of sediment to another. Case in point, beautiful breccias. Look at the angularity of these clasts. And within the middle of it is this lens of sand. That sand gets larger and thicker towards the side and then is gone. If you think about it, if you've got channels coming off an alluvial fan, the channels will erode down to whatever happens to be below. That causes truncations and scouring. A debris flow comes along and fills the channel back in, you end up having gravel sitting on top of sand. So this is probably a small little debris flow. sitting on top of something that's more channelized, and this is just the reverse. All these lateral variations allow you to envision a depositional system where the different facies literally are truncating one another, and that again is characteristic of alluvial fans. All right, anybody have a question about alluvial fans? Yeah.
Were you identifying the channel deposits by the fact that they eroded the layer that they overrided?
That's one possibility, but again, channel deposits, and I don't know if any of these are channel deposits. I think this is more debris flow. The channel deposits here are channels because, see the sedimentary structures? Remember, sedimentary structures denote transport in a fluid media, water. So if this stuff was being deposited as water's flowing down, it's channelized. And the fact that, now this doesn't probably show it all that well because these channels might be several hundred meters wide, but they themselves will be cutting into whatever sediment happens to be below it. It's very hard to show you all the variety in a depositional model that goes on for miles along the base. In fact, that's one of the constant battles that we have, is trying to illustrate things by dealing with the fact that scale sometimes is an important variable here. This, on the other hand, is probably more of a smaller channel. It might even be a fluidized flow that occurred after the gravels were deposited. Any questions? Okay, in the time that we have left, I want to very briefly talk to you about braided streams. And this will be new to most of you, but you have to understand these, again, are very important environments where they can form. We do not have braided streams anywhere where we are. Instead, our river system down here are always meandering streams. Braided streams, unlike meandering rivers, are multiple channel systems. Meandering rivers, this is a lovely shot here from New Zealand. There's a meandering river, standard river looping back and forth. Right beside it, and this is really the neat thing about going to New Zealand and studying the rocks and the systems that are there, because it's such a small but dynamic country, you can literally stand on one depositional system and throw a rock. Actually, no, stand here because braided streams are the ones that have the rocks, and throw back in this direction, side by side. They even almost merge together at a beach, which is itself kind of a neat depositional model. I mean, how can you not love going to a place like this? I mean, I would buy that house right there if it didn't get flooded out every second year. Anyway, so there's the braided stream. Notice one channel looping around, but a lot of other channels. These little kind of ovoid-looking white-colored materials, these are sandbars. In a meandering river, as you should be aware, deposition always occurs on the inside of the loops. Erosion takes place on the outside of the loops. With braided streams, deposition occurs between the channels. And because the water is flowing in a particular direction, you normally get these algon-shaped or eye-shaped depositional systems. Okay? This is a close-up of a river in Alaska. It's a braided stream, and what you're looking at now is up gradients. The water's flowing in that direction. It's flowing very fast. See how fast it's going? Very fast. It's also very cold. There's a glacier up here, and that's where the water is coming from. You do not know cold water until you go wading across a braided stream that is draining from a glacier. And if you're lucky, you'll only have to go this deep. Because guys, there's nothing more painful than going this deep. And you will do it, especially if you happen to be a geologist in Alaska. Now this is a place you want to go panning for gold. Because what's happening here is that the water is transporting down here from a glacier where the glaciers have ripped up a whole bunch of stuff. The water moves fast enough that you can transport pebbles. Not now. This is below flood stage. So what's being transported here is going to be finer grained material, smaller pebbles. But within this, you'll also find heavier material. So not much heavier than gold. So if you want to go panning for gold, you pan in rivers like this. And by the way, panning in a gravelly type environment is not the easiest things to do. Because I mean, talking about pebbles that might be this big and all, to get the little gold bits on is really quite difficult. So plenty of opportunities to go looking for gold in this type of environment. But what I want to draw your attention to now is the idea that these bodies here, we call them sandbars, they're hardly sandbars when they're composed of gravel. Consider that even though this material is being derived from just over the hill, it's being transported in a river that's flowing fast. What would you say about the angularity of these particles compared to the previous ones? Not highly is a speculative thing. Highly rounded occurs on a beach. but certainly much more rounded here than you would have get in an alluvial fan. What about the maturity? No, again, it's at the source of the sediments here, it hasn't gone very far. So this is where you get one of those overlapping conundrums. Relatively well-rounded grains that are composed of very immature materials. You got to be close to the source, but there had to have been a lot of water transport in it. Are you going to find debris flows in here? No, not here. Oh yeah, up here you will, but not here. So you're not going to see any of those massive sediment-supported brecciated conglomerates. Instead, everything here is going to have been deposited in the current. That means relative sorting is going to be pretty good over this. The gravels are all going to be more or less the same size because it's being transported in the current with no mud between them. Debris flows are notoriously poorly sorted. Okay, so right away, even though you're in an area that's pretty close in the same place, you're going to start seeing very fundamental differences between them. And again, the channels here will be scouring down into the bars, and then the bars will be filling in the other things. And I want to also draw your attention, you'll see this in a second when I show you that block diagram which you've seen previously again, but check out the fact that the stream's coming this direction, turns here, bifurcates into two, at one point it's actually turning 90 degrees for the flow of everything else, and then comes around like this. Imagine the paleocurrent directions that are going to be in this type of river system, and how different they're going to be. In this case, that's 90 degrees from that. So if you were to measure paleocurrent indications from this, it's going to be all over the place over at least probably 180 degrees. Net result would still be downstream, but it winds around all over. Now let's talk a little bit about streams and morphology before we go any further, and to put braided streams in perspective of the river system dynamics. When we talk about river depositional models, and when we did this in Geology 111, again, you have to understand we do it simplistically. There are extremes of all of these river types, but we recognize in general three broad types of rivers: meandering rivers, braided rivers, and then between the two of them is anastomosing rivers. This is a relatively new classification. This is where you actually have half meandering and half braided systems within the same river system. So these are all the different styles of channels that we can have. And again, if you thought that rivers were fairly easy to understand, that you get erosion and deposition, like everything, when you look at it in detail, you realize there's a lot of variability. The differences between the type of river you get is largely due to gradient. Now, we already talked about the idea that alluvial fans occur in places where you go from a very steep incline, certainly more than 10 degrees, to a relatively flat incline, like the alluvial plain. Call it 0 degrees, because it's pretty darn close to 0. Braided streams occur on slopes that are steep for a river, but far too shallow for alluvial fans. About 3 degrees is the norm, 3 to 1 degrees. Meandering rivers occur on gradients that are so low we don't even measure them in terms of degrees. We use that standard variation of feet drop per mile of lateral distance. Now, all of you have done that for calculations in geomorphology, right? Where Dr. Allison got you to measure 2 points on a map, figure out how far the river drops. That's your gradient. Did you ever do a gradient calculation for Mobile County? Around here, it's literally about 2 feet per mile. So over 1 mile of distance, the river levels drop about 2 feet. That's still enough for the river water to flow downhill. Gradients for braided streams are on the order of hundreds of feet per mile. So we're talking about gradients that are significantly steeper. Okay? We don't have braided streams here because, frankly, we don't have gradients like that down here. Where do you get braided streams? Draining mountainous areas. That's why I showed you a picture of New Zealand. That's why I showed you a picture of Alaska. And if you want to see some of the world's most classic rivers, you go to the Rockies, where you get incredible stuff. And incidentally, that's where everybody pants for gold. You know, hubcaps up there don't last very long. People steal your hubcaps because they go panning for gold. Just pull off the side. Seen this diagram before, and again, I'm just putting this, I'm not going to go into any detail about this now because, frankly, you should remember this. This was the diagram I showed you when we first started talking about the complexity of facies. So we're coming back to revisit this diagram now. So here is one of the bars that is forming in the channel component. There's one of the bars that formed when the channel was higher. Like all rivers, braided rivers flow higher and lower according to whether they're in flood stage or not. Flood stage in most mountainous areas deals with spring thaw. And one of the most interesting things I've ever done was to go whitewater rafting in a glacially fed braided stream in June. Lovely day. We're all sitting there getting suntans and all, and the water was like so cold, even the rubber of the raft started to shrink up in sympathy. And then, of course, when you're in one of these things, they have like a bunch of different rafts all going down, different companies, and it's traditional to ambush each other. So we went under a bridge, and a whole bunch of guys from the other team were just throwing water bombs at us. It was cold, and then we started throwing things back at them, like oars and sandwiches, and someone threw a fine bottle of champagne for some reason that still escapes me. And one guy, this is so funny, one guy who was from a tropical part of the world, he was one of my classmates as an undergraduate student, he did this and he fell over in the water. And you know those things about how they say in the past people could walk on water, not necessarily Jesus, but people could walk on water if it was necessary or not? I've never seen anybody do that before, but he hit the water and you could just see his face go kind of like, this is not good. And through some power of resurrection, he just miraculously rose up out of the water, ran across the water like this, and jumped headfirst into the raft. And all he said along the way was, cold, so cold. Anyway, it's well worth doing. If you go to Taos this year, I know many people in the past have actually done whitewater rafting down the Taos River. It's well worth doing, but it's just not the same. I mean, the water's like 55 degrees. That's not the same as being water that's at the freezing point. It really is worthwhile. All right, so just again to show you a couple pictures up here, showing you again some of the gravel bars that are in here. And these are kind of neat too, because these are gravel bars, and when the water levels drop low, you can walk across these bars. You'd be amazed how much indication there is of current flow. I have seen large current ripples formed with gravel. Now you can do the math on this. You can do those charts I showed you with Eulson's diagram. You can figure out what current velocities approximately were needed to take gravel this big and deposit it into large current ripples. And this is the place also too where you get significant amounts of imbrication of pebbles. Now imbrication is when you take a pebble that's discoidal, and that's the best type, or ovoid, and they tend to line up so that they're in a stable configuration according to the current. Okay, so if you have a pebble that looks like this, all right, that's kind of flat, when the current flows over top of it, it tends to align itself like this. All right, so all the pebbles tend to do this, and if you measure the orientation of these things, you can determine which way the current was. Now, this is kind of similar to what we did with measuring paleocurrents in the field with ripples and large current ripples, except for ripples, you measure the down dip direction of the lee side to determine which way the current was. Here, it's the opposite. The dip direction shows you the up current direction because the currents always flow downstream. All right, and I spent many an hour measuring these damn things when I was a graduate student assistant. And I show you this diagram here because I just want you to get an idea of just how dynamic these systems can be. These are a couple of diagrams that come from, I believe... Well, I lied, actually. This is... I think this is modern. Well, maybe it isn't, actually. Maybe this is the reconstruction. Anyway, you want to look at it. The arrows you see here are showing you the paleocurrents of imbricated pebbles. And I thought that this was based upon a modern sediment study that was done on what's called the South Saskatchewan River, which is the classic place we're looking at braided stream systems. The other classic place is New Zealand. And in those areas, what they've done is they've actually mapped out the distribution of all the pebbles, showing you the way the currents have changed, and every one of those arrows is probably showing you countless numbers of pebble imbrications. Now, the reason why I'm a little bit hesitant here now, I can't read this because it's really fuzzy, and the citation I see here is for It says deep sea and fluvial braided channel conglomerates, a comparison of 2 case studies. And I'll have to go back and check that diagram out, because this might actually be something that's a little bit more ancient than I thought. It might be a reconstruction of the depositional model. Anyway, I want to look at it. Point is, you can do an awful lot of work here measuring current flows just by the way the pebbles are all arranged. Now, in sedimentary sections, again, the thing to note here is that you're going to see a lot of gravel. So when you look at composite sections like this, you will see things that are in the gravel facies. And look, see here's the dynamic again, using GT, GM for gravel facies, S for sand facies. But notice that because these deposits are water-laying, sedimentary structures dominate them all. Even within the gravel surfaces, you see trough cross bedding. Tell me again what trough cross bedding signifies? Which way is the current flowing? Towards you or into the chalkboard, okay, or in the projection board. You don't know until you actually dig up that third dimension. By the way, digging the third dimension in a gravel bed, don't bother. It's just not worth it. And of course, you start seeing parallel laminations up in the sand deposits. Think about what this means. Gravel is deposited under a certain speed of conditions. Sand is deposited under what? Faster or slower currents? Probably slower currents. Within this, you see trough cross bedding, which represents large current ripples. And then on top of this, probably upper plan bedding. What does that tell you the currents are taking place here? No. Ripples are a lower flow regime structure. Upper plan lamination is a higher structure. But notice there's mud on top of it. And I know why you said it was slowing down, because it clearly looks like you're getting to finer sediment. So you're right, it probably is slowing down as a current. What's the other variable that controls the type of sedimentary structures, though? Water depth. So what's happening? A more likely scenario is water depth is reducing. You go from a state when the water's deep enough that this flow regime is lower to temporarily an upper flow regime status as the water continues to drop, and then you're in a point where it's only mud being deposited. That, folks, is interpretation based upon common sense. All right, and of course this is what you described in the field. This is what your summary diagram showed for you, and from this you make that interpretation of a gradually waning flow. So this whole thing here might represent one spring melting cycle on a river that was receiving its water primarily from a melting glacier. Got it? Okay. All right, with that being done, let's just call it quits at this point. All right, a reminder.